Hello my dear students, welcome back to Fluid Mechanics lecture series. I am your SumamMiss. My channel name is also SumamMiss. You can watch my videos on my channel. Gradually varied flow, as we had discussed earlier, it's a steady non-uniform flow in a prismatic channel with gradual changes in its water surface elevation. It mainly occurs due to the change in the size and shape of the cross section of the channel or due to the sudden change in the bed slope. We have learned previously about the formation of M1 profile and M3 profile for a mild slope channel. So M1 profile mainly occurs due to the obstruction in the form of weir or dam, whereas M3 profile occurs mainly due to the lifting of the gate in a reservoir, and M2 profile forms due to the sudden cut in the bed slope. Since flow characteristics varies gradually varied flow occurs for a long distance. The dynamic equation of gradually varied flow, that is dy by dx equal to S0 minus Sf divided by 1 minus q square t by Ga cube. So the computation of gradually varied flow profiles involves basically the solution of the dynamic equation of GVF. So the main objective of the computation is to determine the shape of the flow profile. So what is the necessity of computation of length of gradually varied flow profile? So whenever we are constructing a dam across the river, it rises the water at the upstream side of the dam. So if we are not giving enough protection to the sides of the river, the water overflows to the river bank and it will destroy the other structures. So that is why, as a hydraulic engineer, one has to determine the length of this water surface profile. So length of the flow profile is calculated from the point of disturbance. So how will you find out the starting point? So the length of the flow profile is to be calculated from my starting point. That starting point is called control section. So control section is a section where a definite relationship between depth of flow and discharge exists. In the direct step method, the channel is divided into short reaches and the computation is to be carried out step by step from the control section. dx equal to delta E divided by S0 minus Sf. This is the principle of this direct step method. So we have to calculate delta E between two sections, and that delta E divided by S0 minus Sf will give you the distance between the two sections. So this method we can apply continuously from section to sections. Then we can compute the total length of water surface profile L equal to sigma delta x. The accuracy of the computation increases by lowering the value of dx. So let me explain this method by solving a problem. So in this problem, length of the water surface profile is determined by direct step method. So in this problem, a dam is built across a stream of rectangular cross section which carries water at the rate of 5 meter cube per second. So due to the construction of the dam, depth of flow upstream of the dam is increased by 2.5 meter. The width of the channel is given as 3 meter and bed slope is given as 1 in 4900. The channel is lined with concrete. N value is given as 0.015. Now we have to determine the length of this water surface profile from the control section to the point where the depth is within 10 centimeter of normal depth. Before applying direct step method, first step is we have to classify the slope. Then we have to identify the water surface profile or type of profile. Then we have to define the control section. Then we have to compute the length from the control section step by step. To start with, we can note down all the data. Discharge is given, width of the channel is given, N value is also given, S0 is available. Since it is a rectangular channel, we can calculate the discharge per unit width, that is small q equal to q by b. In order to classify the slope, we have to determine yn, that is a normal depth or depth in the uniform flow condition, and the critical depth. So before construction of the dam, the flow in the stream, that is uniform flow. Since gradually varied flow is a steady non-uniform flow, continuity equation is valid, that is q equal to area into velocity, or we can apply Manning's formula because n is available. minus equation B, that is equal to 1 by n r raised to 2/3 into s naught raised to half. Q equal to A into velocity, so velocity equal to Q by area, that is equal to 1 by n r raised to 2/3 into s naught raised to half. Area equal to B into yn because the flow is in the uniform flow condition, and R equal to A by P, so that is equal to 3 into yn divided by 3 plus 2yn. So that is area divided by vectored perimeter. Now by substituting this equation, V equal to Q by A, that is Q is given as 5, so Q divided by area, that is equal to velocity, which is equal to, so 1 by n into R raised to 2/3 into s naught raised to half. So by solving this equation by trial and error, then yn obtained as 1.95 meter. For this rectangular channel, critical depth can be calculated as yc equal to cube root of q square by g. So discharge per unit width equal to 1.667 meter cube per second per meter. So yc obtained as 1.415 meter. So in this problem, yc equal to 1.415 meter and yn is 1.95 meter. Yn is greater than yc. So that means this channel is a mild sloped channel. And due to the construction of the dam, the water level here rises to 2.5 meter. Since y is higher than yn and yc, the profile is M1 profile. Since it is a mild sloped channel, the flow is subcritical flow, or you can check by calculating foot number. So always subcritical flow is controlled by the downstream control section. So this point is treated as the control section. So the computation is started from this point towards the upstream side, and the equation is dx equal to delta E divided by s naught minus sf. So length of the water surface profile is to determine from 2.5 meter, that is from the control section, to the point where the depth is within 10 centimeter of normal depth. So normal depth is 1.95 meter. So the destination point equal to 1.95 plus 10 centimeter, that is 0.1 meter, that is equal to 2.05 meter. So the difference in water level between the control section to this destination point, that is equal to 0.45 meter. So in order to calculate the length of water surface profile, this difference is divided into 3 subdivisions as delta y equal to 3 dy or dy equal to 0.15 meter. So dx equal to delta E divided by s naught minus sf. Now what we are going to do is we are going to select a section which is with a level difference of 0.15 meter with respect to the control level. So that is equal to 2.35 meter, which is at a distance of dx1 from the control section. For these two sections, we have to calculate the specific energy and the corresponding sf. By substituting this equation, then we can calculate dx1. Again, we can take another section with a difference of water level of 0.15 meter from this section. So that section is with a flow depth of 2.2 meter and it is a distance of dx2 from this section. So again, we can calculate the specific energy at this section and sf and apply in this equation. Then we can calculate dx2. The final depth, that is equal to 2.05 meter, and for this section also we can calculate the specific energy and the corresponding sf, and by applying this equation we can calculate dx3. Now by summing dx1, dx2 and dx3, we will get the total length starting from this control section to the point where depth is 2.05 meter. So we can use Man's equation for the calculation of sf. So this calculation is better explained by referring this table. The starting depth is the depth at the control section, that is equal to 2.5 meter. So for this depth we have to calculate area, perimeter and hydraulic radius and velocity and corresponding specific energy. So we have to also calculate the sf at this section. So that is the starting section, and the same calculation we have to proceed to this flow depth. So that is for 2.35 meter. So we have to continue the calculation up to this point. Then we have to calculate delta E. So this delta E is the difference of specific energy between these two sections, and between these two sections we have to calculate the average SF. So average SF is calculated, then dx between the two sections is calculated by dividing this delta E by S0 minus SF average. So dx1 obtained is 1710.6. Similarly, for the section between 2.35 to 2.2 meter, we have to continue the calculation of E. Then we have to find out the delta E between these two sections, and we have to calculate the average of SF between these two sections, that is this value. Then by dividing this delta E by S0 minus SF bar will give you dx2 as 2244.2 meter. So the same calculation we have to continue for the flow depth of 2.05 meter. So dx3 obtained as 3749.9 meter. So by adding all these dx values, then we will get to the length of the water surface profile as 7704.8 meter. So this is the length of the water surface profile from this control section to the point where the flow depth is 2.05 meter. So this method is very simple, and the accuracy of the computation increases by lowering the value of dy. Now the session comes to an end. So in the design of the open channels, it may be necessary to calculate the flow pattern for getting the water surface profile and the length or which backwater effects due to the construction of the dam or any other hydraulic structure. Illustrated the concept by solving a problem. For the time being, it is enough. Thank you.